Okay, so hello everyone. I'm very excited to have Carola Doerr today as our speaker. So I think probably most of you people know her. Just as an information, she is an DNRS researcher at Sorbonne University in Paris. And her research interests lie in mathematical and empirical aspects, mostly for black box optimization techniques, and now going more into online algorithm configuration. And today she's going to talk about hyperparameter optimization and algorithm configuration from a black box optimization perspective. And so without further ado, we are very excited to your talk, and the stage is yours.
Great. Thank you very much, Jovita. Very happy to be here. And yeah, thanks a lot for giving me the opportunity to present some work. Jovita knows it already, but I will have to leave at 5 sharp. So I'll try to be brief and on the other hand, I can't see you, so if you have any questions or you want to interrupt me, please just unmute yourself and just jump into the presentation. I'll actually be happy to hear your questions or comments. Yeah, so maybe just a bit of an unusual talk for this seminar series, because I'm not really an AutoML person, if you wish, but I consider myself more as an optimization person. So how come I'm invited to this seminar? Maybe a little bit of history. So my first encounter with AutoML was back in 2016, so 6.5 years ago, when Heike Trautmann and Holger Hoos and Frank Neumann organized a Dachstuhl seminar on automated algorithm configuration and selection. And they invited people from the, let's say, AutoML community and people from the optimization community to bring the two together. And when you see the list of attendees, you will recognize quite a few names. And maybe there are some names that you may not recognize because they may be more into the optimization community. But the goal was really to bring people together and to see where there are potentials to work together, or to use, for example, AutoML for optimization, or to use optimization for AutoML. Because, as we will see also in the talk, the two concepts, I mean, there's some natural points where intersection points of our communities. So this was this seminar, and then was the first time I learned about AutoML and in particular automated algorithm configuration and selection. And yeah, well, my impression of AutoML at the seminar, some people know it. It was a bit like, My impression was that in AutoML, what we do is we try this, we try that, and then we cross our fingers and, oh, it works. Nice. And then we're happy. And then we applaud ourselves and we're happy from having good performance. But my impression was also that we don't really understand what is going on, and we often don't really understand why a certain technique or why a certain algorithm works well, and why our system recommends it, or why we choose this configuration over another configuration. And maybe my impression was even that people didn't really care to understand, but people really care more about having good performance. Yeah. So if you're already upset with me after 2 minutes into the talk, then hang on. I'll be happy to talk about this, and I'll try to give an explanation for why perhaps this was my impression back in 2016. But since I'm here today, you can already anticipate that my mind has changed a little bit about AutoML and the potential for optimization. But back then, this is how I thought about AutoML. And so who was I at the time? So my background really is in black box optimization. And since this is an AutoML seminar, I want to very, very briefly introduce it, even though I think all of you are actually working on black box optimization already. So first of all, we do optimization. So we have the classical optimization setting. We are given a function f that we want to optimize, meaning that we want to find a solution such that the quality, or sometimes I would say fitness, of this solution is as good as possible. And now the specialty of black box optimization is that we don't really have access to this function that we're trying to optimize. So this is a black box. And all we can do is we can propose a solution, like y in my case. And then what we will do is we will run some simulations or some physical experiments, or we will conduct a user study, or do whatever we need to do in order to assign some quality to this sample y. So we somehow want to compute what is f of y. And then, so this way we learn about our problem instance f by what we call this sampling, evaluating, and then learning or adding this new knowledge into our trajectory data. And then using this information that we have, we come up with a new solution z, we evaluate it, we receive f of z, and we continue until we are happy, or in most cases we won't be happy, but we simply run out of time and we are asked to stop, and we need to report the best solution that we have found. So this is black box optimization. And well, okay, so the key objective, just there's one thing I want to mention here, is that what we're really trying to do is we want to minimize the number of queries that we do. So in black box optimization, we typically use as a main performance criterion the number of queries that we do, or the number of evaluations, the number of times we query. But I think for the purpose of this talk is not super important here. But maybe it's nice for you to know that we have a quite simple actually performance measure. So we want to use as few queries as possible to find an as good solution as possible. And well, as I say, all of you know it because you're working in black box optimization, even if you don't know it, because in machine learning, and in particular in AutoML, we do have a lot of black box problems. So we typically, we do not really know, for example, how a certain algorithm performs with different configurations. Or when we think of neural architecture search, or when we think of other AutoML applications, then typically we need we need to guess somehow what are good algorithms. We evaluate them, and then we get some sort of feedback, and then we do this kind of loops, and all of this is black box optimization. So we do have applications in machine learning, artificial intelligence. We also have lots of applications in biology, for example, or in engineering domains, like think of placing wind turbines in the field, so in order to maximize the power production. And you may say, but don't we have formulas to describe it? Yes, we do, but we have very complex interaction between the windmills. And in order to really fairly evaluate it, what people do is they run large simulation models to estimate the power that these wind farms will produce. And okay, while this is the classical case for applications of black box optimization, I just want to mention two other applications. And one is that maybe we do know f, and maybe f isn't really a black box, but so we know what the problem is that we're trying to optimize, but maybe we don't know how to solve it. Yeah, and there are quite a few famous examples, like, I mean, think SAT solving or traveling salesperson problem, where we simply don't really know how to efficiently or how to best solve these problems. And we often then resort or we apply black box optimization algorithms, even though the problem itself is not black box. Yeah, and often when you go and talk to people in industry, they may simply not have the time to develop very algorithms that are very specific to their problem, but they just don't want to apply something off the shelf, and then they use black box optimization. They are happy with the result, and then they continue and go on with their other problems that are waiting for them. And the third application of black box optimization is perhaps we do know f exactly, but we don't want to share it. Yeah, so think of privacy, think of this as, like, for example, we have some medical data here about different patients, and you want to predict something. I don't want to disclose all my data to you, but I allow you to query something. I will evaluate it for you, and then I will just give you some kind of score for what you have guessed. So that's another application domain of black box optimization. Okay, so now this is black box optimization. As I say, you all know it. And what is a hot topic, and what was already a hot topic in 2016, and what has been a hot topic actually for more than 50 years now, I think, in black box optimization, is how is the choice of parameters. Yeah, because our algorithms typically have quite a few parameters that allow us to steer their behavior. And typically, when we apply black box optimization algorithms, what we typically want to do is we first have no clue what we want to do. Like, let's say this is our domain in which we can sample for good solutions. Then maybe we sample a little bit, we sample this one, we sample this one, we sample this one, and so on. So we call this exploration because we don't know really what to do. We explore the search space, but then maybe we see that we have quite a few good solutions here in this region, and then maybe we want to focus the search more in this region, and we call that exploitation. And again, exploitation is something that I think everyone working in machine learning also knows, because we have very similar problems in machine learning. Okay, so now we have decided to sample in this smaller space, for example. Then we sample, we get more information about the problem. We decide to focus even more in this region. Maybe we sample, we decide to focus, and so on. And this behavior, like where to sample, that is somehow controlled by these parameters that determine the behavior of the algorithm. And we want to choose these parameters dynamically. Yeah, so it won't be the same behavior all the time, but it changes during the optimization. Yeah, and the holy grail, if you like, in black box optimization, so what we are all striving for is to find a way, a data-driven way, to automatically choose the parameters that steer the behavior while we are optimizing. Yeah, and I think that is something that machine learning can and in particular AutoML again can very much relate to. It's, I think, but I mean, a goal that we have in common, I think. Okay, so just one like technique, don't be afraid. I mean, I won't go into very technical content today, but essentially, I mean, we could describe this problem as what we really want to do is we want to control the distribution from which we sample our next query or our next solution candidate. And so what we really need to do is we need to control this distribution. But luckily, yeah, we don't really need to be math cracks in order to, or geeks to understand how to change these distributions, because typically these distributions are implicitly given and modeled by a few hyperparameters. Yeah, so for example, you can think of local search, where we simply have a random one parameter that determines the radius at which we sample for new solutions. Yeah? And maybe in the beginning we want it to be large to explore, and then we want it to be smaller and smaller as we continue with the search. Then there can be other other parameters, like for example the probability of accepting a solution that is not as good as the previous one, or if you think of evolutionary algorithms, for example, it could be the probability of making a crossover between solutions, and so on and so on and so on. Okay, and in evolutionary computation or in black box optimization in general, we call this parameter control. Yeah, and so we really want to control we don't want to choose the parameter once and then run it for the rest of the optimization process, but we really want to control it while we are optimizing. And I mean, here I'm simplifying a lot, but there's three, I think, main approaches to parameter control. One, and probably the most simple one, is the scheduled control. So we have a purely time-dependent selection of the parameters. Like here, for example, in this curve, we may say, for example, okay, for a certain amount of time, I'm choosing this parameter value. Yeah. And after whatever 30 steps, I will change this value to another, this parameter value to another value, and then we go on. Or you may say, okay, I don't like this like zigzag. I want it to be smooth. So maybe after every iteration, I update my parameter a little bit. Or maybe I want to update it very aggressively in the beginning and then a bit lighter towards the end, and so on and so on and so on. And as you can imagine, there's like tons of research papers about this kind of scheduled control policies. And one of the most successful algorithms, for example, that does that is simulated annealing. Yeah, I think it is one of the most successful black box optimization algorithms whether we like it or not, but it is extremely successful, extremely well known, and it's extensively used in practice, and it uses such a schedule for controlling the probability of accepting inferior solutions. But if we look at it, then as machine learners, but also as optimizers, we shouldn't be really happy with this, because we don't really use feedback from the optimization process, right? We only look at how much time has passed, and then we choose the parameter value. And this is super unsatisfactory in my opinion. So what people try to do is they try to have systems that are more reactive to what they see. So we really, like in this picture, we very closely follow what the algorithm is doing in order to control the parameters and in order to control the behavior. So for example, we may consider, did we make progress in the last iteration? How much progress did we make? How much progress did we make in the last window of iterations? How diverse are my solutions? Am I sampling closer and closer and closer, or am I still exploring? Like, we can measure quite a lot of things about our optimization trajectory, and we can use that to then determine a good parameter value. And so, like, just to illustrate this, let's say we have a parameter value p, and then some event happens, like for example, yes, I do find a better solution in my iteration. Then I will update my parameter to b times p. And oh, I didn't find a better solution. Then I will update it to a times b. Yeah, this would be a very, very simple rule. But in optimization, it's fantastic. I mean, I could give a whole presentation just about this, but I won't. Is that such super simple rules can be extremely successful. And so this is self-adjusting control. And then the third mechanism that I want to present is learning-based control. And here we model the parameter selection problem as a multi-arm bandit problem. Yeah? And essentially what we do is, maybe it's better with this illustration here. Let's say we have 4 different parameter values that we can choose from. So let's say search radius 1, 2, 3, and 4. And we have different confidences that we assign. So for example, maybe we are very confident that this one is a good value. We have a bit more doubt about this. We have quite a bit of doubt for this. And we really believe that 4 is not very good at all. And then we sample according to these confidences. We have some probability to sample a value. Maybe we choose r equal to 2. And then we do one iteration of the algorithm. We see whether we were successful or not. And depending on how successful we were, we will update our confidences. So like in this iteration, probably what happened is that we got a really, really big advantage. Like we found a much better solution. So we will increase the probability to sample 2 in the next iteration. And we decrease a little bit the other probabilities. Or maybe here increase this, but we decrease for 4 and for 1. Yeah. And it's a little bit like, I mean, I put this picture here because I was looking for learning and this is what I found, but I think it's actually quite good to remember because it's a little bit like we have a pile of papers that we want to read when we do literature research. And it's, I mean, I think we all know this problem, but then we need to choose which paper we read. And then what we do is we typically skim a little bit through it, and then quite after a very short amount of time, we need to say, okay, this is, I will look more closer into this paper, yes or no. Yeah, and this, do I invest more time or not, is a little bit like assigning these confidences into applying it again, yes or no. Okay, so the way I presented it, I think is pretty clear that I don't really like this scheduled control because it doesn't use feedback, but I'm really, really excited about these two because they work well. And so this is this topic of parameter control. And at the time I went to this Dagschul seminar where I met AutoML people for the first time. I was very much into parameter control, yeah, and we had quite some nice results, I think, to present. And essentially what I wanted to discuss at the Dagschul seminar was that parameter control is really nice because it helps us find optimal parameters on the fly. So if we have no clue how to set the parameters, yeah, we don't know, then we can just try, and with these control methods, while we're optimizing, try to learn a good value. Yeah, so that's pretty cool. And the other advantage is that not only we find good parameter values, but we are able to actually track them and to benefit from not using the same value all the time. But we do have situations where we can actually prove also that you have a speed up or a performance gain that is not just a constant factor, but even super constant, meaning you are really benefit a lot from changing the parameters over time. Okay, so we had like what I think, and I still believe are quite nice results about parameter control. So I went to Dagstuhl. I mean, we had these findings. I was super excited. Then this Dagstuhl seminar came, and I was like, oh, cool, there are people doing learning and machine learning, and we had this learning-based control mechanism for which we had a proven bound that it would optimally control the parameters. And yeah, I was super excited. And when you see the picture from this Dagstuhl seminar, you see me smiling here. So probably this was before I gave my presentation, because like the reaction of the people was a bit more like, nobody really knew what to do with my kind of parameter control and with my results. And I mean, the optimization people did, but the machine learners, let's say, I didn't have the impression that it was very interesting for them. And why is that the case? Maybe now I understand a little bit better. First, because there was no really meta learning involved. Yeah, because in parameter control, what we do is we just run the algorithm, and we only look at what happens during this run in order to decide what to do next. But we don't really try to learn from similar situations. Yeah, and I think this is what in machine learning we want to do, is we want to use all the knowledge that we have and transfer it or apply that knowledge to our new situation that we are now in. So I think this is the first reason. And maybe second reason is that people back in 2016, they was very busy with algorithm configuration, static algorithm configuration. So finding good parameter values for algorithm, but like the idea of like dynamically choosing them, it really wasn't a thing back at the time. I think people were just not thinking about it or didn't know how to do it. Yeah? And if we look at what happened since then, I think there have been quite a few game changers. So this is why I'm also here, is to say, yes, I think it's actually quite nice to see in 6.5 years how much this whole attitude and perhaps also our like technical abilities have changed. So there was a series of papers which I think show the potential of using machine learning and optimization and bringing those two ideas together. So to control but to use machine learning techniques in order to do it smarter than what we did how we do it in a pure parameter control setting. So there was at the Gecko 2019 this paper by Mudita Sharma and Manuel and Alexandros and Dimitia, I don't know really, but Manuel, I think, is a person who's very well known in the community. What they did is they applied some reinforcement learning in order to learn by sampling instances from some distribution. They tried to learn typical situations where the algorithm can be in, and then try to learn, okay, what are good parameter values when I'm in this situation? Yeah, and they do that with a lot of, like, let's say, computational power. As you know, I think reinforcement learning quite expensive, but they somehow managed to learn good parameter control policies. And so this was 2019. Then there was there's a very nice PhD thesis by Andre. I don't know if he's here because I can't see a list of participants right now, but there are probably some people from Freiburg in this team who have also worked on this. So what in Freiburg they call dynamic algorithm configuration, and in Hannover, sorry, I should mention as well. So this is the PhD thesis of Andre, and there are two papers associated to this. There are quite a few more. You can go into the PhD thesis, but I think the first one was really this EKI 2020 paper, where they introduced or formalized this idea of dynamic algorithm configuration. So it's essentially formalization of what Manuel and others have done here to give it like a formal framing, and they also then subsequently show different applications where they could also successfully learn good control policies. And there's this recent journal paper. I think if you want to know what has happened since then, I think this is a very good reference to read. And then we also worked at this. So there's Diederik Vermetten and the whole group of Thomas Beck in Leiden. We worked on this problem as well. So starting with this work on online selection for CMAS variants. And then there's also work by Anja Jankovic, who was a PhD student in my team, and Anna Kostovska and Tomi Eftimov and others. So we work on what we call a per run algorithm selection technique. So we run optimization algorithm, and then every now and then we ask ourselves, okay, should I change? Should I use a different algorithm, yes or no? Or should I change the configuration of my algorithm, yes or no? And then if so, how, which algorithm should I use? And so on. And all of these works, even though they use perhaps not always the same techniques, but I think all of them really try to use machine learning, or in particular AutoML, but to somehow integrate it into this black box optimization algorithm, and to make the selection of the parameters a bit smarter. Okay. So now this is my background, and now what I really wanted to do is I wanted to talk about a few challenges, and since we don't like challenges, but maybe opportunities for AutoML in this whole area of black box optimization, in particular with respect to algorithm selection and configuration. So here I called it algorithm and parameter selection because I didn't want to call it dynamic algorithm configuration, and you will see in a second why. And I think it's not only for dynamic, but it also actually holds for static algorithm selection and configuration. And first thing I think is that, so we have this work, this dynamic algorithm configuration work, which phrases essentially parameter control as a machine learning problem. So we assume that we can, actually train a policy to choose the parameters while we're, so that we can assign to each state a parameter value, and that we can train this policy that maps the state to the parameters while running it many times. And as you have seen, with reinforcement learning is one of the key techniques. It's super expensive. Yeah. And in optimization, unfortunately, it's very often not the case. We don't have the time to do that. So in optimization, we very often face this problem that we're given a problem instance, and we don't have the time to train, or we don't have possibility to train, because it may be very expensive to run the algorithm, and we can only afford one run of the algorithm. So we really have to do that online. But on the other hand, what we do have is we do have a lot of data, right? I mean, you guys in machine learning, and we in optimization, I think we're doing a lot of benchmarking. So we have a lot of data, performance data, instance data, and so on. We just somehow need to be smart and make better use of this data, and not retrain models every time for every possible problem, yes or no. And like in the optimization case, we are essentially ignoring all this benchmarking data that we have, and we are just always, each and every time we run an algorithm, we let the algorithm configure itself while running without really looking into the benchmark data. So what I think would be like the holy grail would be a combination of the two approaches. And really is that, I like this picture, so thanks Anja for providing it, so that we are optimizing a problem, say, and we are getting better and better and better over time. And then maybe we're here at this point, and we ask ourselves, okay, how should we continue? Which configuration should I use, or which algorithm should I choose? This one, or this one? And then at this point, we say, okay, stop a minute, or a second, or a millisecond, but let me just check with all the data that I have, yeah, what that data would recommend me to do. Yeah, maybe I should choose now a local search algorithm with a search radius of 5. Or maybe I should use a differential evolution with this and this and this setting. Or maybe I should switch to Bayesian optimization and use a surrogate this and this model and this acquisition function. Such kind of decisions. Yeah. And I think we should really, really, really value all the data that we have. And I think that is something we don't really do at the moment. We are all happy to have a lot of data, and when we submit papers to our conferences, we're even required to make it accessible and so on. But if you look at how many people are downloading the data, 0 or few, right? So I think there's really a lot of missed opportunity, in my opinion, is to try to really learn from all this data that is out there for our settings. And I think there are two ingredients that, in my opinion, need to be further developed. One is warm starting techniques. So this is in particular important for when we want to switch from one algorithm type to another type. So if you're in machine learning, then you probably know Bayesian optimization, and you probably apply that a lot. And you may know that Bayesian optimization is pretty good for very expensive problems, because when we have low budget, we typically have very fast convergence in the beginning. But then we also probably know that when we continue optimization, and often what we observe in Bayesian optimization is that we have this very, very good learning curve at the beginning, but then it kind of flattens, and then Bayesian optimization fails to improve as time goes by. And CMA, for example, a very popular evolution strategy, is the other way around. Yeah, so typically we observe that it is very slow at the beginning because it needs to set its parameters right. But then once it is correctly configured, you have very good convergence. So we really have a complementary behavior. We have this Bayesian optimization that is super fast in the beginning, but then quite flat in the end. And we have CMAS, which is different, like slow in the beginning, but then super fast once it is correctly configured. So now it seems pretty obvious that it would be cool to combine the two problems and to use Bayesian optimization here while it's super good, but then somehow switch to CMAS and profit from this steep learning up from here. So if you could combine the two, then, I mean, hopefully we will get even better performance. And obviously we are not the first to observe that, but actually many people have tried that. And there's some papers here that I mentioned that try to do that, to go from the Bayesian optimization to CMAS. But when you look into the papers, it's a little bit, I mean, the first two, for example, it's a little bit frustrating because I mean, the results are good and they get it going in some settings, but I think it doesn't really exploit the full potential. And why is that? Because essentially what they do is they run the Bayesian optimizer for some time. And then when the moment that they switch to CMAS, they essentially start a new CMAS and just center the first distribution. But all of the information that we have gained already during the optimization process, they don't take it into account. So I think there's a lot of wasted potential. So the third paper here by Rudolph and colleagues, they try to be much smarter than that. So they try to really take the full trajectory and try to use that information that they have gathered in order to like warm start the CMAS, the distribution, with more information. Yeah, and I think there's a lot to be gained by looking into this, and by perhaps not only looking at, as I said before, into this one particular run that we are optimizing, but actually making use of that big treasure of data that we have in order to then really warm start CMAS or whatever algorithm we switch to, so that it can right away perform well without having to self-configure for too much time. And another thing, I think, where we have a lot of missed opportunity at the moment is that we all like benchmarking, we all produce a lot of data and we like to share it, as I say, but people don't download it. And what's the problem? Why are people not downloading it? Because we use very different ways of storing the data. And I think we have all experienced that it's very hard without standardization of data, or even agreeing on what kind of data we want to keep track of. Maybe the data that was produced by this other group A and Y is not useful for me because it is missing something, or it is just stored in a weird way. So it will be much faster for me to just rerun everything using my own system, so I can be sure and I know exactly what they have done. And I think this is a big waste. I think that is something that in optimization we have the advantage of having quite standardized benchmarking systems and environments that are compatible with each other. So we produce data that is compatible with each other, and this I think is good because it really gives us this big treasure that we can exploit. But one thing I think that is a bit undervalued at the moment is a systematic annotation of this data. So in order to fully exploit the potential that we have in all this data, I think what we need is we really need to systematically annotate it so that we can really operate on this data and really get more information out of it. Yeah, and I think there are concepts like knowledge graphs and ontologies and so on. There's a lot of things that are already developed, but in order to make it happen, we need to transfer or to store our benchmarking data in such a systematic way. And here we're working with Anna Kostowska, for example, and then Tome and Sasho and many others on optim. That is an ontology to do exactly this for benchmarking data in optimization. So if you think that you like to try to apply your AutoML techniques to optimization, then the good news is that there is a lot of data and there's a lot of standardized data. So it's not just that you would have to go and collect data everywhere, but everything is already like quite standardized and available. Okay, so this is one aspect or one topic I'd like to propose as something where we could actually work together, and what would really like to see more work is this setting where we have where we don't really have the opportunity to train, but where we do observe data, and then we want we do observe the progress that we make while we're optimizing, and then using kind of all of the benchmark data that we have in order to decide what to do next. And another topic I want to propose as being super interesting for working together is benchmarking of AutoML techniques for problems with known ground truth. And this is something that was quite nice collaboration with Nguyen Dang at St. Andrews and Andre and Frank at University of Freiburg, is where we took some black box optimization problem for which we had a proven optimal control policies, and we benchmark AutoML techniques, in this case reinforcement learning, to see, does the reinforcement learning system, the AutoML system, does it actually manage to find the optimal control policies? Yeah, I think we had this nice subtitle here, when theory meets practice. Whether this is really practice, I don't know, but I think we are at least getting a little bit closer here. And I think there's a big, again, I think there's a big opportunity here to use results where we have proven optimal policies to challenge your AutoML techniques. And so I won't describe the problem in great detail, just to say that what's nice about this framework that we propose is that you can change quite a few parameters. You can change the dimension of the problem. You can change the portfolio of the actions that the algorithm can or that the policy can choose from. You can change the size of the portfolio, but you can also change like the composition of the portfolio and so on. And we have a very, very simple notion of state, which is just like the quality of the current best solution. And as I say, we really know what is the optimal policy here. And then we can use that optimal policy and we can benchmark the in this case, we benchmark DDQM, so reinforcement learning techniques. And we see here, for example, one example where actually DDQM was quite fast and quite efficient in, or I mean, I don't know, it depends on your scale, but it actually managed to find policies that are good, very good even, and very close to optimal or even optimal. But then there are other situations where it's really oscillating a lot. And even though it does find very good policies, it doesn't really stick to them and it behaves weirdly. And we even observed settings then also where it didn't converge at all, like it just flat very, very bad solutions and it doesn't manage to find good ones at all. And what I like about it is that not only do we challenge ourselves by having a ground truth against which we can compare, I think it also helps us to better understand what is going on. And like this, what I said before, is it looks a little bit like magic, AutoML, who it works, to really gives us an opportunity to understand why it works and when it stops working and perhaps why, because we can go and maybe check, for example, is it a problem dimension that is a problem? Is it the portfolio size? Is it a state space? Is it this or this? Or is it a noise? Is it this or this? Because we have quite a few levers that we can change. So all in all, I think this is a great opportunity to work together. If you don't, I mean, if you're brave and you're willing to challenge your AutoML techniques, then I think we do have a lot of problems for you where you can challenge your systems. Maybe it's also a good moment. I think this is recorded, so maybe I shouldn't say that, but after this Blackbox seminar, for example, I went back home and what we did is we tried hyperparameter optimization techniques. And I was curious, I wanted to know, and I said, okay, why don't you configure a 1+1 EA, just the mutation rate? So very, very simple problem even if you don't know what is an EA and so on. But one of the most simple problems you can think of, in our opinion, and the results were terrible. Yeah, and again, I could say a long story, but I think such cases are good to understand how would a user approach or apply our system. Maybe they get results they are not happy with. Why is it that they are not happy with? And is it a problem it's too difficult? I think no, it was not the case at all, but maybe there's some assumption that is different, or you need to tell the users something in order to make it work for them. Okay, now I'm coming to an end. One more opportunity I want to mention is that, again, this comes back to this, like, we do a lot of magic and then, look how wonderful it is. That I don't like, is that one opportunity I see is to derive explicit formulas to describe the instance parameter setting mapping. Yeah, so in our automated algorithm configuration, I give you an instance, you do your black magic, and then you tell me which parameter value I should use without telling me why, right? And so there's this work that we did with Mohammed and Marcella and many others that I think goes a little bit unnoticed. And if you look at it, you may probably find it cute because it's a tiny application, but I think the key ideas behind this are quite nice. And I don't know, I mean, I'm proposing it here because I hope some people would get interested in this. And here the key idea really was that instead of just having my instances and my algorithms and then asking my AutoML technique to propose some parameters to me, to compute some explicit formulas that would map the features of the instances that would really give me, okay, for these kind of features, I would propose this parameter for you. And for these features, I would propose this parameters for you, but that these functions here are not black box, but that they are explicit. So we did that kind of using a genetic programming approach over symbolic regression and so on, blah, blah. But in the end, what we wanted is that we don't propose 0.02 for n equal whatever, 100 and 0.015 for n equal 200. But what we wanted is that the system gives us some results, some explicit formula for how I should choose depending on the feature of my problem. And in our case, the feature was simply the dimension, so we only had a single feature. So that's why I'm saying it's pretty cute and perhaps not, people don't get too excited about it at the moment, but I think there's a lot of potential here, is that we compute explicit formulas that can express how the parameter value should depend on the instance feature. Yeah, because then it's not black magic anymore, but we offer an explanation to the user why we have chosen this or that. Okay, so let me just summarize. So what my goal really is to understand why or how different algorithms in black box optimization complement each other, and complement each other for different instances, but also all along the optimization process. Yeah? So that we go from this static selection of algorithm to like a dynamic choice and adjustment. And so we do that by analyzing, of course, how the algorithms do, and we do that with different techniques. But the goal really, and my dream maybe, is that in the long term, we develop techniques to auto-select and auto-configure the algorithms. And ideally, this is the last point that I mentioned on the previous slide, we would do that not as a black magic style, but with an explicit and hopefully even easy to understand rules that to recommend this or that algorithm or this or that parameter value. And then one thing I didn't spend a lot of time on here, but I scratched it briefly, is that I think one more objective, in my opinion, should be is that we don't develop only these tools, but if we actually make this knowledge also available to practitioners. So if you know me, you may have heard about our project iWedge Profiler that we use to standardize benchmarking. I work with Navigrad, where we have a lot of a large collection of optimization algorithms, but also optimization problems. And then I mentioned already optim, our ontology to really systematically store the benchmarking data. And yeah, I mentioned these three opportunities that at the moment I find really exciting to work together, and where I see a lot of potential. And yeah, I'd be more than happy if anyone in this audience would be interested in exploring more, come talk to me and to the team. I think we're all equally excited as I am to do research on this. Yeah, and with this, yeah, I'd like to hear also your thoughts or comments about this application or possible application for AutoML. Thank you very much.